Okay, large center location. So this is applicable to only orthographic views. The center of an arc with a large radius is difficult to show in true position, and the dimension lines are shortened, but the values are true location and radius dimensions. So if your radius is so large that it doesn't fit on the paper, you can do these foreshortened versions of the leader lines. The value shown, though, should be the true location of where the center point is. Okay, foreshortened radii. This is applicable only to orthographic views where there's no true shape seen. So in the example on the left, you're looking at a half-inch radius, or 500,000th radius, but it's on an angled surface. So you're not looking straight on at the arc. Okay, so the view is actually going to show somewhat of an ellipsoid. So you can dimension the true radius of the arc dimension in a foreshortened view of an arc, but you have to precede the R with the word true on the radius dimension so that it's making it clear that the view is not reflective of the true angle, but that the dimension is of the true size. Okay, features on a curved surface. They can be located by an angle, a chord, or an arc length method. They are difficult to control features and locations. I had a project that I had to make an inspection tool for something that was dimensioned back in the 1970s to an arc length measurement. And so we built a functional tool to check the part, and without it, it would have been difficult to check this part. And it was bigger than the CNC machine, so we had to make the tool in different segments. Okay, spherical radii. The spherical radius is in front of the dimension, SR, and the leader terminates with a dot on the surface of a model or an arrow on the edge of the profile on an orthographic view. Irregular curves. So curved surfaces made of tangent arcs, dimensioned by showing locations and sizes of arcs. And the surface is best defined by model geometry or a reference to a mathematical file, if not common geometric shape. So I've worked in aerospace for quite a few years in the past, and we had airfoil shapes that were defined by formulas or data tables, and that was imported into the CAD software, and that defined the plotted points defined the shape at a certain cross section. So if it is a complex shape, it's pretty difficult to document it with dimensions like this. Okay, symmetrical features. In the latest version of the standard, they actually got rid of the geometric control for symmetry. It's very difficult to hold true symmetry. It's different than saying I'm going to make an opposite of a part. You're saying that on both sides, tolerance-wise, it needs to meet this very tight tolerance. So if you shave a little off one side, you got to make the other side the same. And but if you are using symmetry, only half the symmetrical part requires dimensions in a partial orthographic view, so you don't draw the whole thing. And dimensions for symmetrical features must be relative to the line of plane or symmetry, so that has to be drawn on the drawing. And symmetry is indicated by two short lines across each end of the center line, denoting symmetry across that line. And large parts shown in partial views or halves are acceptable. But I would discourage you from using that convention. Round-ended bars. Fully rounded ends have a radius tangent to the two sides. So this is for bars of material. The radius half the distance between the two tangent sides, and partially rounded ends have a radius always greater than half the distance between the two sides. I think what they're talking about, two sides, are talking about the diameter of the bar. Okay, slotted holes. Used when tolerances accumulate between parts to prevent fasteners from passing through round holes. And dimensioning method depends on the design function. So you have the option to go end to end, notation, or center to center, as is shown below. But it depends on the function of your device. Slot in location models. Established by model geometry in undimensioned models. And standard method of showing slot location in fully dimensioned model is dimensioning the location of the slot center. Key seats. So a key seat is a feature put in rotating shafts to mate them to whatever they're hooked to keep the item from spinning. And you typically have bolts or a press fit holding the part on, but the keyway is a rectangular piece that goes in a slot in both parts to keep it from rotating. They also are designed to shear off at a certain torque to protect the machine from itself. If it were to seize up, that shear key will shear off and then allow whatever the device is to freely spin without damaging a motor or drive system. And it can be replaced. So it's a slot or pocket cut into a shaft or hub. The depth is usually dimensioned from the far side of the shaft or hole. Profile tolerance applied to the control depth if dimensioned from center. And position tolerance must be applied to the width dimension and is not to be assumed to be perfectly centered. So you need to dimension that. Narrow spaces. Small adjacent features require several dimensions in a small space, then extension lines close together may break when crossing arrowheads, as shown on the left. You can also use what's called a joggle in the extension line in an orthographic view. It allows clearance between adjacent lines without disconnecting extension line from the point of application. So shown in the lower image, you've got a joggled extension line. And larger scale detail views may be necessary to avoid having to do this, or so that you can even see the difference on them. Later, I'm going to be talking about a different kind of joggle, but in this context, the word joggle is being used in reference to those extension lines in the offset extension line graphic on the left. Center drilled hole. Okay, the hole on a countersink cut into the end of a shaft or other cylindrical feature, and it's created with a combined drill and countersink tool called a center drill. Standard center drills have a 60-degree countersink, although you can buy them at different angles. And the center drill size is noted by specifying the number of the center drill to be used, and it's number 1, 2, 3, 4, 5. And I believe the smaller the number, the bigger the center drill is, but I have to double check that. And I would consider this a tooling hole, so it's something that needs to be put in a cylindrical part so it can be manufactured. What happens is on a lathe, you would put what's called a live center or a dead center, which has a taper on it of 60 degrees, and it puts pressure on one side of the part, centering it, and the opposite side's in a chuck. Okay. Machining reliefs. So you may need to put in reliefs that provide an area for the cutting tool to travel and be stopped without damaging the tool or the part. That's specified in a note or dimension detailed view that it's machining relief. And the relief width, depth, and fillet radius must be given. So an example is you're trying to turn threads right up to a shoulder. You need to cut a relief so that the tool has room to finish the helix and retract. Okay, threads. Very common feature for machine parts. Minimum information given is the nominal size, threads per inch, thread form, and thread class. The example on the left is a 750 thousandths, 10 threads per inch UNC with a class 2A thread. Now, I want to note that the examples in the book show decimal inch with their callouts for threads. That is a military convention. It is not used for commercial convention unless it's military application. This is a 3/4 inch by 10 bolts, so it's a 3/4 10 thread pitch, United National course, and then the thread class of 2A is A means it's an external thread, B means it's an internal thread, and the 2 is the middle tolerance range for the system. So that's the thread tolerance you would get from an average hardware store. If you're doing aircraft or high vibration applications, you'd have to get special bolts that are at a 3, and class 1 is for really inexpensive things that need to be assembled quick. So that's in your leveling feet for chairs and I don't know, patio furniture and that kind of stuff. Okay, the thread depth, if it does not extend through the part, needs to be called out. And the distance is a fully formed thread extends into the part or feature. So you often have a hole that's drilled deeper than the fully formed thread, so you don't break the tool that's going into the hole. Knurls, they're machined on cylindrical shape. This is one type of knurl. It's called a diamond-shaped knurl. There are other types of knurls that are straight. They're machined on cylindrical shapes to increase friction between parts that are pressed together. That's one application. Or to improve the grip on a handle, like on a wrench. Or improve the appearance of a part. I've seen them on aesthetic, even towel racks and things like that. Give them an industrial look. The diameter dimensions before and after knurling are required for a shaft that's going to fit inside another part. Otherwise, you don't have to have that. Okay, sheet metal bends. Two intersecting lines located by extending flat surfaces that lie on the same side of the sheet metal. Specify either inside bend radius or outside bend radius. You have to specify the bend radius, the material type, the thickness, and dictate the opposite side of the radius if that's what you intend. Typically, sheet metal is dimensioned from inside radiuses. Tends to be how the equipment works. But you can, if you have a special application where you need to do an outside, just make sure it's clearly noted. Okay, joggles. This is the other form of joggle. This is a sheet metal joggle. They're used for transitions between offset surfaces. So you see this where you have multiple panels on something and they need to interlock with each other. The joggle will be the thickness of the material so that overlapping sheets can go together and be fastened together. Also increase strength. It's often seen on sheet metal parts. It's not to be confused with the extension lines we talked about earlier, even though the shape is similar. And you have to give the dimension by giving location, height, length, and bend radius. Okay, standard sizes and shapes. So companies can come up with a standard of size shaped items, or perhaps there's a specification for hardware that's standard shapes and sizes. So it reduces the production cost and need for special operations if you have standard size shapes. There's no need to dimension all the features on a standard part. The part number can give the information you need. So for example, below we've got a standard piece of stock. It's a standard diameter. The abbreviation STK follows after it, denoting you don't have to process that surface. And then you've got a length that's specified it's going to be cut to. On the right, we have a 1/4 20 UNC 2/8 screw. and it's an inch long below the head, and it's a socket head cap screw. So there's a standard for that. And individual company standards may define features or parts as well. Okay, broken links and orthographic views. They're not permitted on models. Long parts broken into a portion removed to reduce required drawing space. Dimension used to show length, not broken. Dimension value, size to be fabricated. Limits of size. All dimensions, excluding basic dimensions, must include tolerance. The amount of variation allowed. Size dimension tolerances applied to dimensions or feature. And maximum minimum allowable size based on applicable size tolerances or limit dimensions. And created when size value has tolerance applied to it. Limit dimensions. They specify a minimum and maximum acceptable value with two numbers. The difference between them is the tolerance. The maximum limit is written above the minimum when both is shown. The minimum limit precedes the larger in a node and is separated by a dash. Plus and minus tolerances. So a unilateral tolerance allows variation only in one direction. So it's either plus or minus value, and either the plus or minus value is 0 and the other value is a number, as shown on the example on the right. It is limited to 875 plus 0 minus 2 thousandths. Bilateral tolerances allow variation in both directions. So the example on the left, we have, they can be equal or different. So we have 876 plus 2 minus 1. Class, listen to me. Don't use these. Use a symmetric tolerance. Make it easier on your machinist. Do the math so that your end product will work, function the same, at plus or minus the same value, and model your parts at that nominal value. Otherwise, you're setting these guys up to be an offset. They're really going to have to try to shoot to be halfway between those numbers anyway. So it's convenient for the engineer, but the engineer can do a little more calculating, I think. Okay, single limit dimensions. They're only acceptable when second limit control by part geometry. Okay, so in this case is a radius of, they don't care how big it is or how small it is, it can't be any bigger than 30 thousandths. Okay, tolerances on angles. Not recommended to specify with limit dimensions or plus or minus tolerances. It can be, but it's not recommended. We use geometric controls now. Orientation and profile tolerances recommended for defining allowable variation on angles. And single limit is not practical and not used. So you wouldn't say 45 degrees max or min.